In our previous video on plastic additives, we discussed about different additives which are used to enhance the performance, appearance, and reduce the cost of plastic products. In this video, I will talk about dispersion and distribution of plastic additives, which are very important to manufacture high quality products. I will also discuss different processing parameters that help to achieve desired dispersion and distribution of additives in polymer matrix. Several additives, as listed here, are used to enhance the performance, appearance, and reduce the cost of plastic products. During product manufacturing, it is always desired to achieve the best performance at lowest possible additive loading, because a higher amount of additive will add to product cost and also may lead to deterioration of other properties. So, it is always important to use an optimum amount of additive. To find the optimum amount of additive, we first must make sure that additive is compatible with the polymer matrix. Processing conditions are selected to minimize degradation of additive, and desired level of additive dispersion and distribution is achieved. Achieving desired level of dispersion and distribution is very important to extract best performance from an additive. So first, let's try to understand these terms, dispersion and distribution. Imagine you are the class teacher and have a box of chalk. You want every student to have one chalk. You called a student and gave him the box. What will you tell the student? I guess you will tell him to distribute the chalk among the students, not to disperse the chalk among the students. So, when we are distributing something, we are keeping its physical form intact but increasing the spatial distance, like moving them away from each other. Now, if you want students to use the chalk to color the water, what you will say to student? I hope you will say disperse the chalk in the water, not distribute the chalk in the water. So, in case of dispersion, we break it into smaller particles, but particles can remain very close to each other. So, dispersion is breaking a large particle or agglomerates into smaller particles, and distribution means moving individual particles away from each other. In industry, several additives are sold in the form of beads and master batch. One such example is carbon black. In bead or master batch, these additives are present as agglomerates. Therefore, during product manufacturing, it is important that the beads or master batch get fully dispersed and distributed in the polymer matrix. As we can see here in the first picture, when additive in the form of bead and master batch is fed into the extruder, they are in poor dispersion and distribution state. Next, depending upon the mixing parameters, two things can happen. Either the beads will move away from each other without significant reduction in their size, or beads will break into smaller individual particles but remain in the close proximity. In the first case, we will get uniform product due to good distribution, but we will not utilize the full potential of the additive as dispersion is poor. In the second case, although the additive's surface is fully utilized, but the product is not uniform. In case of reinforcing filler, in both scenarios, there will be several weak points in the final product. So, the ideal scenario will be achieving both good dispersion and distribution. And this ideal scenario can only be achieved by using appropriate mixing parameters and screw design. Now, let's discuss different parameters that affect dispersion and distribution of additives, and how we can select them to achieve desired dispersion and distribution level. Before discussing about process parameters, let's first try to understand the mechanism of dispersion and distribution. During melt mixing, dispersion takes place by two mechanisms called rupture and erosion. Rupture mechanism is breaking of large agglomerates into smaller pieces, and it will depend on the amount of shear stress and melt viscosity. Usually, lower viscosity is better. On the other hand, erosion is removal of smaller particles from the surface of a large agglomerate. The extent of erosion will depend on melt viscosity and mixing time. Here, higher viscosity is better. So, additive dispersion will depend on amount of shear stress, melt viscosity and mixing time. So, if we want good dispersion, we have to select compounding parameters and screw design which will allow us to have higher shear stress, optimum melt viscosity and longer mixing time. Similarly, distribution of additive will depend on flow pattern, melt viscosity and mixing time. For distributive mixing, lower melt viscosity is better. So, for distributive mixing, we have to select screw design to provide turbulent flow and compounding parameter which will allow lower melt viscosity and longer mixing time. Good thing is, both single and twin extruder are sufficiently versatile to achieve desired level of dispersion and distribution. Now, let's first discuss how to achieve good dispersion and distribution in single screw extruder. In single screw extruder, there are three levers: process parameters, screw design, and mixing elements that can be pulled to achieve desired level of dispersion and distribution. In single screw extruder, the shear stress depends on the flight depth and screw RPM. The shear force also depends on the melt viscosity of the polymer, which can be changed by changing the temperature. So, by selecting the specific screw profile, RPM and temperature, we can increase or decrease the applied shear stress and thus achieve desired level of dispersion. On the other hand, the flow pattern and mixing time can be changed by changing RPM, screw design, viscosity and mixing time, which depends on the screw length. Therefore, by optimizing process parameters, we can achieve desired dispersion and distribution of additives. Some specific screw elements can also be used in the single screw extruder to increase dispersive or distributive mixing. Some of the screw elements which are used to enhance dispersive and distributive mixing is shown here. Incorporation of blistering rings, Madoc and Egan mixing sections helps to increase dispersive mixing. Similarly, the flow pattern can be changed by using pin or pineapple type screw and thus achieve better distributive mixing. One of the examples of screw design to achieve both good distributive and dispersive mixing in single screw extruder is shown here. In summary, we can say that in single screw extruder, process parameters, screw design and mixing elements can be varied to achieve desired dispersion and distribution. Now, let's discuss about twin screw extruder. Twin screw extruders are much more versatile than single screw extruders. The two screws used in twin screw extruder can rotate in same direction or in opposite direction, which will lead to significantly different level of shear force. Similarly, two screws can be intermeshing or non-intermeshing, that will also lead to significantly different level of shear force. Finally, most twin screws are modular in nature. As a result, infinite number of screw configuration can be used to achieve different level of dispersive and distributive mixing. Some of the elements for distributive and dispersive mixing are shown here. It is beyond the scope of this video to get into the details of each element's design and how they lead to higher shear and different flow behavior. But in general, dispersive elements either increases the shear stress or makes larger volume of material to pass through the higher shear zone. Similarly, distributive elements allow more turbulent flow and reverse flow, thus improves distribution. These elements can also be arranged in a specific pattern to further increase the dispersive and distributive mixing. Here is the summary showing how design and staging angle of kneading block affects the dispersion and distribution of additive. A wider lobe provides higher dispersion by increasing the amount of material passing through the higher shear zone. Similarly, lower angle leads to higher shear zones. However, if there is more leakage, it will lead to better distributive mixing than dispersive mixing. In most instances, the presence of dispersive and distributive elements leads to lower throughput, which is not desirable as it will lead to higher product cost. So, elements are selected to achieve a balance between quality and throughput rate. Therefore, optimization of process is so important. Till now, we said that both good dispersion and distribution is required to achieve the best performance. But in some specific application like carbon black, things can be little different. Carbon black is used as both color pigment and conductive additive. For color application, excellent dispersion is required since color depends on the light absorption, which is directly related to exposed surface area. But if it is used for conductive application, which requires formation of a conducting path, we would not like to have excellent dispersion, because if it is in excellent dispersion state, then individual particles will be equally distanced from each other and there will be no conductive path formation. Therefore, in case of conductive application, we need moderate dispersion but excellent distribution of carbon black. Also, in some other case, like for shear and temperature sensitive additive or to minimize resin degradation, we may also need to customize the mixing process to achieve either higher dispersive or distributive mixing. In summary, we can say that there is significant difference in dispersion and distribution of additives in polymer matrix, and both are important to develop high quality products. The extent of dispersion and distribution can be controlled by processing parameters and screw design. In most cases, optimization of process parameters is required to achieve a balance between quality and cost of the product. In this video, we mostly talked about the general approach to achieve desired dispersion and distribution of additive, but specific requirements for a specific equipment and additive can be different. So, optimization is required for almost all systems. If you have any question, please reach out to us. Thank you for watching this video.